Let us start lecture 43, and the course is on phase diagrams in single component and binary systems. And today's topic will discuss on isomorphous phase diagram, and we'll see how to calculate it using some numerical values. In fact, if you see in the last lecture, we have got formulas to calculate equilibrium compositions of solid and liquid solutions at a particular temperature, and that equation will be used for calculation of phase diagram in case of germanium silicon system, and there will be using 4 data: melting point of germanium as well as silicon, as well as enthalpy of melting for germanium as well as silicon, and see what data we achieve. Okay. Now, let us start doing that. So, if we check, we are talking about isomorphous phase diagram in a binary system, and we will take germanium silicon system and see how we arrive at those equilibrium compositions at a particular temperature. Now, for that we need Tm germanium, which is equal to around 1211 Kelvin. So, everything should be taken, the temperature should be taken in Kelvin, please understand that. Now, delta H m naught germanium is equal to 36,940 joule per mole, and if I try to see silicon, for silicon Tm silicon equal to 1687 Kelvin, and delta H m naught silicon is equal to around 5210 joule per mole. Fine. And initially what we have done in the last lecture, what we have done for A and B, and we have taken binary system, and where Tm B is greater than Tm A, and we have derived at the formula, which is x A solid equal to 1 minus exponential minus delta G naught m B divided by R T exponential minus delta G naught m A R T minus exponential minus delta G naught m B R T. So, this formula we got for solid solution at a particular temperature, trying to find out two compositions T equal to 1500 Kelvin. Now, if you see this temperature in between is in between two melting points, silicon as well as germanium, and we can get x A liquid equal to 1 minus exponential minus exponential minus delta G naught m R T minus delta G naught m B R T with a minus sign here into exponential minus delta G naught m A by RT. So, that is the two conditions and two equations, and now this is with respect to A. So, that means what we will get. So, if I try to draw the phase diagram, so this is, let us say, silicon side and this is germanium side. This is 1687 Kelvin, this side is 1211 Kelvin, this is 1500 Kelvin, and this side is temperature. This axis is temperature, this axis is X silicon. So, this axis would be X germanium. Okay. Here pure X silicon equal to 1, this side X germanium equal to 1. These are the two pure sides. So, we should get a composition around here and around here. So, this is X A liquid and this side would be X A and this side would be X A solid. Okay. That is what we get, and this is one extreme point, another extreme point is this. In fact, if you do all other temperatures between 1687 Kelvin to 1211 Kelvin, you should get a curve like this, and that would give you isomorphous phase diagram. So, our interest is to calculate these 2 points, okay. And you follow it up at different other temperatures, you should get all those points like this, different temperatures, all those points like this. But our interest is this temperature. We will be using this formula. Now, when we do that, if we see A and B, melting point of B is greater than melting point of A. So, then silicon can be considered as TMB, this can be considered as TMA, and here also del H naught M A, and this one would be del H M del H naught M B. Okay. So, silicon would be B and germanium would be A. So, this is A, this is B. So, then everything falls in place. So, now we will try to calculate XAS at 1500 Kelvin. For that, what we will be needing? We will be needing delta G naught M B, which is nothing but delta H naught M B divided by T M B into T M B minus T. So, I can write it as delta H naught M silicon into T M silicon minus T divided by T M silicon. Okay. So, I can get the value which is 50210 joule per mole into this is 1687 Kelvin minus 1500 divided by Tm is 1687. If you this would be joule. Of course, we are talking about 1 mole. Now, if you recall, we have proved this particular formula using using a state variable enthalpy change for solid and liquid, okay, in earlier lectures. So, this would, if you do the calculation, you will see that this would become 5566 joule per mole. Now, for delta G naught M A, which is nothing but delta G naught M germanium equal to, I can write delta H naught M germanium into T M germanium minus T divided by T M germanium. Okay. Now here T greater than T M germanium, fine, because 1500 Kelvin we are considering. Okay. So that case you would see that this would become negative. So this would become minus of 8816 joule per mole. Okay. So at that temperature, the A should be in liquid state. Okay. But as per this formula, okay, if I consider this formula is derived, if you recall, this is H, this is T, this is Cp solid, and this one is Cp liquid, this is melting point. Okay. So if you extend this, we are talking about a temperature here, let us say this is A, fine. So that time we have tried to find out this particular value. Okay. So this is delta G value, we can say naught. So that value actually gave rise to this equation. You just go back and find out, and this is nothing but delta H, this is delta H naught M, not M, now this is at a particular temperature, and this is delta H naught M. So we tried to calculate this value, and similarly we can also do it for entropy, and then we got delta G naught at a particular temperature, it is equal to delta H M naught T M minus T divided by T M. So that way this formula was arrived. Okay. And for that we have taken cyclic rule, and we have equated, and we equated that all the values for every step process we have added up, and then we if you add it up then equate to 0, because that is H is a perfect differential or the state function. So it will lead to 0. So that way we arrived at this particular formula, and there the basic assumption was CPL minus CPS equal to 0, or we can say CPL equal to CPS. So this was the assumption. Fine. The difference in Cp values of solid and liquid, that is 0. So that is what it minus comes. Had it been below melting point, you would have come positive. Okay. Let us now use this formula, use these values, this particular value and this particular value in this equation. Now we can find out XAS equal to 1 minus exponential minus 5566 divided by R is 8.314, R is equal to 8.314 joule per mole per Kelvin. This is a gas constant. divided by 1500 divided by 1 exponential minus of 8816 divided by 8.314 into 1500 minus exponential minus 5566 divided by 8.314 into 1500. Okay, so we have placed that. Now we would get, you would see that you would get 1 minus 0.640 divided by 2.028 minus 0.640 is equal to 0.36 divided by 1.388, which leads to the value about 0.26. So that means for the composition of solid solution in terms of A, which is in equilibrium with the liquid solution at 1500 Kelvin, is 0.26, that is the mole fraction. Now we can get XAL, which is nothing but XAS exponential minus delta G naught M, or let me put it A first, R T this. So A is considered to be, this is for solid solution, composition, and this is liquid solution, composition. So we know that this is 0.26 into, and this value we have already calculated is nothing but 2.028, which gives me the value 0.53. Okay. So the two composition of solid and liquid solutions at equilibrium are basically X, and this is nothing but X liquid germanium, fine, and here also this is X germanium solid. So X germanium solid equal to 0.26 and X germanium liquid is equal to 0.53. You can actually find out in terms of XB. X silicon solid should be equal to 1 minus 0.26, which is 0.74, and X silicon liquid equal to 1 minus 0.53 equal to 0.47, okay, because XA plus XB equal to 1. So that means you got two compositions at that so this value comes out to be 0.26 and this value comes out to be 0.53 in terms of B. Like that way you keep continuing at different temperatures just by calculating these two values and changing the temperature, you get it. And if we go to 1687 and 1211, you will see that there will be one composition would turn out to be 0, another one would be 1. Okay. So, like that way you can find out the isomorphous phase diagram, you can calculate using that two formulas. So, that particular phase diagram what you get, that is completely based on ideal solution consideration, that means Raoultian behavior of solution, and that values may not match with perfectly match with the practically calculated phase diagram, because ideality, that Raoultian ideality is very difficult to achieve at. Okay. So, there will be always some enthalpy contribution, that enthalpy contribution in terms of the bond energies. If we consider binary, AB bond energy could be different than bond energy of AA, that means similar A type bond or similar B type bond, and those will lead to non-ideality in the system, and that non-ideality would deviate the phase diagram from the ideal phase diagram. But in case of silicon germanium, over quite a bit of composition range, the solidus and liquidus, they match each other to a great extent. Okay. So, you can use this formula and calculate, and you can use some of the books or literature or Google, you can Google that is germanium silicon phase diagram, and you can match your result with that data what you have snatched from different books or by doing Google. Okay. So, like that way you can calculate isomorphous phase diagram. So, I just wanted to show how to use that, and there one tricky part is this one. Okay. So, where we have seen that this particular value comes out to be negative, because this temperature is beyond the melting point of A. So, that is what it becomes negative. So, that is what here when you try to see this particular part. Okay. So, this particular part, the exponential minus of delta G m naught A by R t, that term would become positive. Okay. Means inside exponential, that inside of exponential, that part would become positive. Okay. So, otherwise things are all straightforward. So, now let us also discuss one part. For example, while drawing the phase diagram, we have for binary system, let us say A and B, we have taken melting point of B is greater than melting point of A, and with that, and we have considered of course ideal solution formation. This is binary. Okay. So, there what we have done, we have taken for example, at a temperature which is in between T m B and T m A. If you recall, we have taken G A naught liquid, the reference value what we have assigned is 0, G naught B solid is taken as 0, and correspondingly the position of solid A and liquid B in their pure condition are placed on G versus X plot, that is mole fraction plot. And for that what we have done, we have used the free energy hierarchy for pure metals. So, let us say this is my T m B and this was my T m A, and this is G A naught solid, this is G A naught liquid, this is G B naught solid, and this is G B naught liquid. Okay. We can put it in terms of black color, black ink. Okay. So, we have taken a temperature which is in between. This was the temperature what we have taken. So, that temperature, this consideration fits in properly, because B solid B is stable and solid liquid A is stable, fine, at temperature T, at temperature T. So, and then accordingly we got a plot like this. This is 0, this is 0, this is x b equal to 1, x a equal to 1, and this assignment is G A naught liquid, and this was G A naught solid equal to G B naught solid, and let us say this is G B naught liquid. This difference is, let us say this particular value is, let us say 1000, let us say 500, fine, and this is in joule. So, delta G M A equal to minus 1000 joule per mole. In fact, we can joule per mole, and delta G naught M B equal to plus 500 joule per mole, and this is G1 of liquid, this is G1 of solid, fine. And then we have drawn the composition free energy diagram. This is for G2 solid, and for the liquid we got this is G2 liquid, and we got a common tangent which was this, and this is XB solid and this is XB liquid. Okay. So, that is what we got. Now, that time we also mentioned that this particular assignment, this assignment is basically as per the convenience. Now, let me see whether I can assign 0 to solid A as well as liquid as well as now let me do it for, let us say I do it for delta G B liquid, that is taken as 0, the reference or standard condition. So, then let me see whether that is there will be a change. In fact, you will see that there will be no change in that equilibrium composition at temperature T. This is at temperature T. So, if we try to do that, what we will do? We will exactly place so this is 0, we will place it as per these differences. Okay. So, now we have we are assigning G naught B liquid as my reference condition for B side, and we are not changing here on the left side. This is G A naught, this is liquid as 0. So, we will place it G A naught solid. So, this will be placed at 1000 joule, this is G in joule. Okay. And this now correspondingly this particular solid will now be placed 500 joule away from G B naught L. Okay. So, let me place it here. So, this would be my G B naught solid. Okay. And this is minus 500 joule per mole. Okay. So, then of course, this would be, please you make a correction, this can be joule per mole, and in fact, here G is all the time for 1 mole. Here also you can write joule per mole, and G is always for 1 mole, 1 mole condition. Now, if you put it at minus 500, so this difference which is delta G naught M B is still 500 joule per mole, because delta G M is nothing but G naught B L minus G naught B S, and there also it would be, this difference would be minus delta G naught M A, this will be minus delta G naught M A, okay, and delta G naught M A is still minus 1000 joule per mole, okay, because liquid has lower value than solid in case of A. So, the melting free energy change for pure A would be negative. Now, I need to just find out the G1 for solid. So, this one would be G1 for solid, and G1 for liquid would be G1 liquid, okay, which will be the 0 0 line connecting 0 0 point. Now, if I do, so I just would like to extend it just to show that these two compositions are extended, okay, and solid line would be okay. So, G2 solid, if I have to draw, okay, a little fine, and if you draw a common tangent, the common tangent will pass through these 2 points. Okay. So, common tangent is passing through these 2 points, fine. So, this is the point, let me just put it in a different color. So, this point or this point and this point. So, this is still x b solid and this is x b liquid. Now, you see, even if I change the standard reference value for the pure condition, I will get the same compositions at the same temperature which will be under equilibrium. So, this is another important aspect that what reference value you are taking, that would not matter, because finally, we are actually dealing with the free energy difference. So, here we are actually having entire equations. If we try to see these equations are only based on these difference values. So, that finally, that would not make any difference. You will get the same, you will get the equilibrium at the same composition, even if you change the standard state or the reference value for the for A and B, whether you are doing it for solid or liquid. You can actually make another plot where you can keep this side fixed, you can change, you can assign, for that you can make another plot where you can make G A naught solid should be equal to 0, and G B naught solid equal to 0. So, this is condition 1, this is 2 and this is 3. So, you just try to plot that. Remember, when you plot this particular positioning of G A naught S and G A naught liquid, as well as G B naught solid and G B naught liquid, that positioning should be done in such a fashion that this difference will remain minus 1000 joule, and here also this difference would remain plus 500 joule. On the B side, on the B side plus 500, and on the A side it should be minus 1000 joule per mole. So, that you please make sure so that you are maintaining that, then things will be absolutely fine. You will get the similar, you will get a plot where the common tangent will touch the same composition what we have got in case 1 as well as case 2. Case 3 would also yield the same compositions at the temperature. So, let me stop here. We will discuss now the cases where the solution would deviate from a Raoultian behavior. So, that time you would have a contribution from enthalpy while making a solution, and that contribution would have an effect on the phase diagram. And you would see that contribution from enthalpy as well as contribution from entropy, they would compromise each other to give you a typical shape of phase diagram, and that phase diagram we will learn by understanding the philosophy behind it, as well as we will also derive formulas which will allow us to find solid solution line as well as liquid solution line. And after that it is all about finding a composition of solid as well as liquid solutions where the equilibrium will be established at a temperature and fixed pressure, which is the pressure is always kept at 1 atmosphere. Remember, that is what we are using, not here, though in the beginning I have not mentioned. Please understand that all the formulas what we have found out till now for in case of binary solid solution as well as binary liquid solution, these are based on pressure keeping 1 atmosphere. So, let me stop here. Thank you very much.